Hey guys, this is the second video on Chapter 10, all about the ideal gas law and how we can get the other laws from the ideal gas law itself. Now, remember that for gases, there are four very important variables: pressure, volume, temperature, and amount. Now we have a single equation that relates all of these different variables, and that is the most important equation for Chapter 10, the ideal gas equation. As we saw in the last video, that volume and moles and temperature and pressure are all related, and they're related in some way. They're related through some constant, and that constant is R. R 0.08206. Okay, super important there. Liters atmospheres per mole Kelvin unit there. Now, what that gives us is the ideal gas equation, this one here, PV equals nRT. The only thing that you really have to know to get the other gas laws, PV equals nRT, the most important law for gases. Now let's take a look at how we can get those other gas laws from our ideal gas equation, PV equals nRT. So we'll just do a couple of them. We can do Avogadro's law, sure, and we'll do the combined gas law. Okay. Now for Avogadro's law, remember it was V1 over N1 equals V2 over N2. And the big thing there was that pressure and temperature were constant. Okay. So in order to get this from the ideal gas law, all we have to do is get whatever's changing on the same side, on one side, because everything else remains a constant. Okay. So let's take this, divide both sides by n. Okay, to get n on this side, and then divide both sides by p to get rid of pressure on the left side. And what we get is v over n equals RT over p. Now remember that temperature and pressure are constant, so this whole thing has to remain a constant for our system. So no matter what we change in our system, those two things have to be equivalent because they both equal RT over P. For the combined gas law, much the same thing. Remember, combined gas law, moles was the only thing that was remaining constant. So we divide both sides by temperature, and we get PV over T equals a constant, right? N times R. And so no matter what we change, it has to equal this value. And so we get P1 V1 over T1 equals P2 V2 over T2, because both of those equal number of moles times R. Hopefully that makes some sense, because it really is a lot easier if you just can get the equations from the ideal gas law, so you don't have to memorize it much. Boyle's law is probably the easiest because it's already there. Boyle's law, pressure and volume are our changing variables. Moles and temperature remain constant, so this guy is constant. So we get P1 V1 equals P2 V2, because they both are equal to nRT. No matter what, this thing remains constant. So that's getting the other laws from the ideal gas law. And let's take a look at a quick example of just an ideal gas equation. So a gas initially had 2 atmospheres, so our pressure, so we get PV equals nRT. So 2 atmospheres in a 10-liter container. We want to know how many moles there is. We don't know N. R 0.08206 liters atmospheres per mole Kelvin. And finally, we get temperature is 123 Kelvin. Remember, all of our calculations have to be in Kelvin. So we can plug this into our calculator and solve for N. When I do that, I get 1.98 moles. Pretty straightforward, just plug and chug. Now, we do have such thing as standard conditions, standard temperature and pressure, or STP for gases. It's 0 degrees Kelvin, or 270, or 0 degrees Celsius, 273 Kelvin, or 1 atmosphere, and 1 atmosphere. Now, whenever we plug this in to the ideal gas law equation, we want to know what volume a mole occupies. And so for pressure, we have 1 atmosphere. For volume, that's what we want to know. N, 1 mole. R is, of course, R, and 273 Kelvin. Now, whenever we do this and we solve for volume, we get a very special number, and that is 22.4. 22.4 liters per mole. Okay, that's the molar volume of a gas at STP, and it's a conversion factor. It looks a lot like that. Okay, and that's very important for us because if we carry out these reactions at STP, we can easily calculate volume from moles and use it in stoichiometry, just like we did mass-to-mass conversions. Let's take a look at an example. At STP, the combustion of 16 grams of methane produces how much carbon dioxide? So the first thing we need is a reaction. Combustion reaction. Okay. So we've got 16 grams of methane. Now I did this on purpose, so the math would be easy. My molar mass for methane is 16 grams per mole. Carbon's 12, hydrogen's 1. My molar ratio here is 1 to 1. So same thing we've been doing up to this point, right? This is all just stoichiometry, just same stuff we did in 3 and 4. Now, once we're here though, now we can use that special number 22.4 liters in 1 mole of carbon dioxide. Okay, moles of carbon dioxide cancel, moles of methane cancel, grams of methane cancel, and because I chose easy numbers, you get 22.4 liters of carbon dioxide gas that's produced from the combustion reaction of 16 grams of methane. Now that's a very easy example of stoichiometry with molar volume, but we can do all sorts of other ones. We can do limiting reactant, we can do percent yield, we can do theoretical yield, we can use volumes from reactants, all sorts of stuff, just because we have that molar conversion, volume to moles. So be prepared for that and look at some examples there, but it's all the same stuff. It's just the only difference is that we're plugging in liters per mole instead of something like grams per mole, like molar mass. That's it with the ideal gas law. There's some other applications that we'll talk about in the next video, but for the basics of the ideal gas law, that's about it. Now I do want to talk about one quick thing with the ideal gas law. There's a reason why it's called the ideal gas law. Right, the ideal gas law. What the ideal gas law assumes is that the volume, it makes those assumptions that we talked about in the first video. The volume of a gas is 0. The intermolecular forces of a gas are also 0. And what that means is that the identity of the gas doesn't matter. It can be hydrogen, it can be carbon dioxide, it can be carbon tetrachloride. It doesn't matter as long as the we're assuming that it's an ideal gas, the volume is 0, the identity doesn't matter. As you can imagine, real gases in the real world don't always behave that way, and we'll see at the very last video when they don't. A couple of special conditions. But I just want to point out these are ideal gases. They're approximations of the way gases behave, so that it makes our lives a little easier because the identity doesn't matter. Anyway, that's it with the ideal gases. We'll pick up next time with the next video.